Hello, everyone. Welcome to this webinar. Just let's wait a few seconds to allow all the people joining from the lobby, and we will get started. All right, so good morning or good afternoon, depending on where you are joining today. And thanks a lot for being with us for our Cracking Colors with Neutral Atoms webinar. It's a joint webinar hosted by Pasqal, together with our valuable partner, Fondazione LINKS. My name is Lucia Garbini, and I am the community builder here at Pasqal. And I am really excited to be the host of this event for you today. I'm excited because today's webinar marks the kickoff of Quantum Pathway, Pasqal's global webinar series. And I'm really looking forward to have you in all our upcoming events that I will talk about at the end of the webinar. And before we jump into the technical content of this webinar today, let me take some time to introduce to you the partners behind this webinar and this work, and the speakers who were at the core of this collaboration. So Fondazione LINKS is a renowned big applied research center based in Turin, in Italy. Among many national and international projects, they focus on digital transformation in industrial settings, working on fields like artificial intelligence, Internet of Things, and quantum computing, of course. Their really strong quantum team focuses on developing hybrid and quantum algorithms for real-world applications and integrating quantum computers, quantum processors in high-performance computing solutions. For today, we have as a speaker Chiara Vercellino, who is an expert researcher at Fondazione LINKS, part of the quantum team, of course, and she's pursuing her PhD at Politecnico di Torino. Her research focuses on optimization and quantum machine learning applications for quantum computing. So thank you so much for being with us today, Chiara, and welcome. So Pasqal is, on the other hand, a leading quantum computing company pioneering the use of neutral atoms to develop scalable and high-performance quantum processors. Our mission is to unlock practical quantum advantage in many different applications, including, of course, optimization, machine learning, and simulations. Our work is combining heavy research and development together with industrial applications, and this work together with Fondazione LINKS is the perfect example for that. And representing Pasqal with us today, we have Yassine Naghmouchi, who is a senior quantum algorithm developer at Pasqal. He holds his PhD from Paris Dauphine. Sorry, probably my French pronunciation was not that, that good. With a strong background in operation research. And his focus is hybrid quantum classical solvers for complex combinatorial optimization problems. So thanks a lot to Yassine as well to be here, and welcome. So now that I am introduced the two partners in crime for quantum optimization and the speakers, it's time to check what will come next during this webinar. Yassine will tell us a bit more about the collaboration between Fondazione LINKS and Pasqal, and Chiara will guide us through a technical deep dive on the algorithms to solve graph coloring developed throughout the collaboration. We will have at the end a dedicated Q&A session, so please feel free to share your questions in the questions icon that you see on the right bottom side of the screen. and we will make sure to answer your questions. Before I leave the stage to the experts in the room, I would need your help, guys. So I would like for you to join me in a pool time. So this is just to get to know each other, and you see now a question popping up. If your quantum knowledge were measured in qubits, how powerful would it be? I would like to see how many people here can dream in quantum protocols. Let's see. So let's see if we can check the results. Yes, I see that we have quite many 20 qubits. That's nice. And also, yeah, it's quite a broad range of quantum knowledge, which is good. Our event is for all of you guys. So thank you so much for participating in the poll. And now, with no further ado, I leave the stage to Yassine.
Thank you very much, Lucia, for this nice introduction. I would like to thank all the attendees also for joining us this afternoon. What I will go through during the next 5 minutes is the following. I will try to provide you with some elements um, about the collaboration in terms of context, in terms of motivation, and in terms of goals, all from a technical point of view. So we are considering the graph coloring problem. The graph coloring problem is the problem that assigns the minimum number of colors to vertices in a graph in such a way that no two adjacent vertices can share the same color. So this problem is an NP-hard problem, meaning that classically it's computationally difficult to solve it for all the instances. And in the same time, it is a problem with meaningful and significant industrial applications, like register allocation, scheduling, frequency assignment. And from a quantum computing perspective, it's exactly these kind of problems that are difficult for classical computers and at the same time have significant real-world application that we look at in order to highlight the potential of quantum computers to solve them. So this is, I didn't finish the slide. Thank you very much. And now, in order to consider a quantum computation for classical for combinatorial optimization problem, we need, first of all, look at the classical solution method that exists. And one well-known and efficient for a lot of cases solution method is the decomposition method, and in particular, column generation. So the idea of column generation is that you will split your problem to two subproblems. You will have a master problem that will try to minimize the number of colors in the graph. And here, a color, you can see it as an independent set because no two adjacent vertices share the same color. And at the same time, you have another subproblem, which is called generally the Price-N subproblem, that will generate the best independent set to minimize the objective function of the master problem. So when I say best independent set, this means the maximum independent set. So this decomposition in classical optimization has proven to be efficient for many types of instances. And this efficiency can extend to quantum computing, and in particular to neutral atom quantum computing. As we can see in the next slide, neutral atom quantum computing can solve natively and exactly the maximum independent set problem. So it gives a way and technological tools to solve exactly the Price problem. To recall the Price problem, the problem that will generate colors that will minimize the objective function of the master problem. So how it works, I will give you here some general elements on it. So what you will do to solve the maximum independence problem, first of all, you will embed your graph in a register, in the machine. You will use atoms. Each atom corresponds to a vertex. And then if you imagine that you shine a laser in this graph, then each atom will be able to interact with the neighboring atoms within a distance that is called the Rydberg radius. So if two atoms will interact together, you can imagine that you have an edge. And this way, you can embed your graph in the hardware. Now, to have your maximum independence set, what you do is that you prepare an initial state. You can imagine that this state is the state, the Rydberg state, meaning the zero state for every atom, and you will evolve your system to another fundamental state. Now, if you measure your system, you can observe two major observations. The first one is that thanks to the Rydberg phenomenon, thanks to the law of quantum physics, two adjacent atoms cannot be excited at the same time. So what you get is an independent set, actually. Then second, as at the end of the evolution, your system is at its lowest energy state, then what you get is a maximum independent set. So this is how neutral atom quantum computers gives you a way to exactly encode a maximum independent set, and then solving exactly the Price problem, which gives us a framework to have kind of a hybrid column generation. So if we go in the next slide, you will see that previously, Pascal, we have developed a quantum column generation for solving the Price subproblem for solving the graph coloring problem. And on LINKS side, there is also a significant work on branch and bound techniques, where at each node, we sample the solutions using a QPU, a neutral atom QPU. So a natural question comes here: what if we combine the the quantum column generation with the quantum branch and bound? And if there are some optimizers here, they will immediately say it is a branch and price algorithm with, of course, some parts of that branch and price algorithm that are solved using a quantum computer. So this is what we call a hybrid branch and price algorithm. So what Chiara will shortly present to you guys is how we achieved superior performance on hybrid graph coloring with branch and price compared to separately consider the quantum column generation and the quantum branch and bound. I hope this introduction was clear enough for a detailed technical presentation that will be given by Chiara.
Thank you so much, Yassine, for your contribution. It was very enlightening. And now it's time for another poll. I would like to know what you guys are working on. Are you involved in projects with quantum related or optimization related projects? Let's see. I see that a lot of people, well, almost 45% of you, more than 45% are working on quantum optimization in either research or industry settings. We do have people that are planning to start soon. So again, quite a broad spectrum of answers. So, and now it's my pleasure to leave the stage to Chiara. Thank you so much again for being with us.
So thank you so much for this very kind invitation. And yeah, in this few minutes, I'll try to be, let's see, to compromise a bit between the technicality and but still like preserving a bit of clarity in this. So I will start from the very beginning. So the definition of the graph coloring problem, which I guess for most of you is something very clear, but it is useful to set up some notation and some concepts. Then I will repeat some basic principles in branch and price for those of you who are not expert in operational research, and then show you how this branch and price, which is a classical algorithm, can be hybridized with quantum. And so I will guide you through all the main steps which are typical of branch and price. And finally, I will show you some of the results that we got both on emulation that on Fresnel machines. So these are very interesting results because they are amongst the first ones we are having to share with you. So the next slide, please. Yeah, it is the definition of the graph coloring problem. So we are considering a graph which is made of vertices and undirected edges. We call this graph G. And the objective of a graph coloring problem is to find the minimum number of colors, namely it is called the chromatic number, so that we can color all the graph, but in a way that no adjacent vertices, so vertices that share an edge, are colored with the same colors. In the figure below, you just see an example of it. So you see a graph with 5 vertices and the corresponding edges. And you see that in this case, we have an optimal coloring with 3 colors, the one shown in the figure. And we see that the chromatic number so is 3. Also, and this is the most important thing to notice, is that each color is an independent set. And by independent set, I mean that all the vertices belonging to the being colored with the same colors do not share an edge, so they are non-adjacent. This allows us to provide a mathematical formulation of the graph coloring problem. In this case, like, you can formulate this problem in several ways. This is the way that is more convenient for us to define the branch and price algorithm. So you have your graph G. By S, you denote all the independent sets of G, and you want to find the best ones. So among all the possible independent sets, you want to find those that allows you to cover the whole graph, but you use the less number possible of it. So this is what the objective function, the minimization over the sum of ZS variables brings you. You can see here that in this case, ZS, the variable, are binary variables. So this is an integer program, which is by nature very hard to solve classically if the dimension of the variables increases. Also, it is important to notice that if we consider all the independent sets of a graph, we can end up with a very large number of variables. This is why usually from this formulation here, you move to another kind of formulation, which is on the following slide. Okay, thank you. Which is the one that we see here. And what we did in this case is that we relaxed the problem. So we have no more binary variable z, but we have a continuous variable z. And this is instead problem easy to solve classically. So we can feed it to classical solver and obtain a solution in a very fast time. This problem also has what you call in operational research a dual problem. So while we solve the primal problem, we also solving the dual problem. And under the condition of the strong duality problem, so theorem, so that both the primal and the dual problems are feasible and admit an optimal solution, we have also an equivalence between the two optimal solutions. But still, like if you imagine solving the primary problem I was showing you before with a classical solver, you still want integer solution because you cannot use continuous solution. You cannot say that one node of a graph is colored, I don't know, like 40% of one color and 60% of the other color. You want integer solution. And usually, like if you just go, for instance, with a traditional branch and bound approach, you still have that very high number of variables. So the ZS variables, which covers all the possible independent sets of a graph, which means that you might end up exploring a very huge solution space. So this is where the branch and price algorithms kicks in. It tries to reduce the number of variables so that you explore only the most relevant one. How you do it? You have still your master problem, which is the one you see on the left. But the duality theorem provides you also with a prices subproblem, which is instead the one on the right. Which means with the optimal solution of the dual problem that you obtain from the relaxed version of the master problem, you can have those the solution of those variables W's, the optimal solution of those variable W's that can be used to define the prices subproblem. And you see that this is a kind of problem that we really like with dealing with neutral atoms, because it is actually a maximum weight independent set. You see there that you're trying to maximizing the number of vertices in your graph G. You try to select those that provides the maximum weight, because to each vertex you have assigned a weight. You don't want that adjacent vertices have the same colors, and those are cut out by the first constraints. And you have, in this case, binary variables. And this is like a very elegant in the mathematical point of view, because you can see that if you simplify things on one side, for instance, like relaxing the master problem, you still have the complexity, which is just transferred to the prices subproblem. But in this case, it is very useful because it's kind of problem that we can tackle with the neutral atoms quantum technology. Once you solve the prices subproblems, then you have a solution, which is the maximum independent set. And if the related cause, actually in this case is a reward, the RS, it's less than 0, it means that that set is valuable. So if we add that the set S tilde to our previous master problem, then we can improve our coloring solution. Now we can move to the quantum part. Actually, Yassine helped me and so explain you a little bit of this, so maybe it will be easier to follow me on this. This is Pasqal technology. So you have your rubidium atoms arranged in a 2D array, and you have your atoms that can assume the ground state, so the 0 state, or the Rydberg state, so the 1 state, to like provide you with an association with optimization. You can imagine qubits stay in the zero state to be like variables with value 0, and those staying in the Rydberg state like variables in the value 1. And if you have just one qubit, then you hit it with the lasers, and according to the parameters delta and omega, which are the tuning and the Rabi frequency of the laser, you can switch the state of the qubit from the ground state to the Rydberg state. So from the 0 state to the 1 state. But the things can become more complex if you have 2 qubits. And in that case, there are 2 possibilities. So if the 2 qubits, so the 2 atoms are far apart enough, then they can both assess the Rydberg level, and so they can both end up be in the 1 state. If they're close enough instead, actually closer than the specific distance called the radius, which depends on the parameter omega and delta, then the Rydberg state, so the state in which they both assume value 1, that is not accessible. And so you can either have one being 0 and the other one being 1, or vice versa. If you extend this concept to a whole register, then you have that the Hamiltonian that is driving this quantum system is the one reported here in the formula, and that since we are measuring the states of the qubit along the z-axis, then we are actually measuring that an I operator, which basically counts the number of qubits which are in the state 1. And so in this picture here, you can see that I have 8 atoms, because indexes start from 0, and only those that are closer than the Rydberg radius have the circles that intersects. In this case, the circles, the green circles have a radius which is half the Rydberg radius. So whenever they intersect, it means that they are closer than the Rydberg radius. And you can see that the Rydberg effect prevents atoms closer than the Rydberg radius to be both in the state 1. And so actually, while you make your system evolve according to the parameters omega and delta, if you end up in the ground state, then you know that the solution is actually an MIS solution. MIS stands for maximum independent set solution. So in the next slide, yes, thank you. This is just an example of how we can solve this MIS problem, which in our case is the crisis subproblem using Pulsar. I know this is probably a very dense code. I will not go through all of it, but you first define the register, which defines the way in which represents your graphs. So you assign position to atoms, which means assigning position to vertices, and that allows you, by defining the sequences, which is determined by the parameters omega and delta, to define also the Rydberg radius. Then you run the simulation and you extract a dictionary of results. We'll see an example later in the results slide. And this dictionary of results is actually the variable x. The variable x we were mentioning in the formulation. You compute the reduced cost S and decide if the identified independent sets are valuable candidates or not. So with this, we have the first two key elements of our branch and price algorithm. So the definition of the master problem and the column generation. Then another important step is to define the primary heuristic. The primary heuristic allows you to obtain a feasible coloring solution, which is an integer solution, and that allows you to have like an upper bound to a specific, given a specific set of independent sets which plays the roles of the columns or also of the colors. So in this case, we have designed a very naive heuristic, but it is fine because we don't need to have a very smart heuristics. We have whole the branch and price process for that, which basically relies on the columns extracted by the price subproblems and define a feasible coloring, which is then the third element of our branch and price algorithm. After that, we have all a series of elements which actually reminds you of trees. The first one is the branching, and this is the branch part of the branch and price algorithm. So we have a way to define the nodes of the branch and price tree, and then we need a way to define branches. How do we branch? So how can we reduce the space of the solution? We can do it by branching on these columns generated by the branch and price, by the prices subproblem. So at each step in the branch and price tree, we have an induced subgraph G, an induced subgraph H, which is a smaller, it is a subset of the vertices of the original graph G, an objective function which is actually given by the primary heuristic, and the primary heuristic plus the branch selection, because maybe the next slide is a bit more clearer. Let's suppose that we have original graph G, BE, so at the root of the branch and boundary, H is equal to G. Then we run a first round of the prices of problems, and we obtain, for instance, 4 sets, S1 up to S4. Let's suppose that S4 is not a feasible independent set. So we have S1, S2, S3. For each of them, we branch. And for instance, if you look at the highlighted branch and price node was said before. Thank you. Then we have that induced subgraph H is actually the original graph G by removing all the vertices that were in S1 and maintaining the same, maintaining a subset of the edges, which is E prime instead of E. And then on the green node, lighted green node, you run another prices of problems, and you obtain S5 and S6, and you keep on branching with those. As you can see, this can lead you to a lot of a lot of branches. So we need the bounding so as to allow the pruning. Concerning the bounding, okay, thank you. Since we are doing a minimization problems, because we want to use less color as possible to color a graph, we are interested into looking into lower bounds. Literature provides us with a few lower bounds that are computed accordingly to eigenvalues of the adjacency matrix A or the inertia of it. Also, the master problems, you remember that one that was obtained by relaxing the z variables, that also provide us with a feasible lower bounds. And so we can select as a lower bounds for a node the maximum among all the possible lower bounds. That guarantees us to have a stricter lower bound as possible. Why are those bounds so important? They are important because for the pruning criteria, which is the third element of the branching part of the branch and price algorithm. Basically, the pruning criteria allows you to reduce the solution space, and there is, in our case, there are two. One is, let's say, a very standard pruning criteria. So you compare in each node of the branch and price the value of the lower bound with the best current objective function. If the lower bound is greater or equal than the best current objective function, it means that you won't be able to find a better solution if you further explore that direction in the branch and price tree. And so you can prune those subsequent branches. We also added another one, which is the pruning criterion by redundant solution. You can imagine that if you start with a graph with a number of nodes and you start removing them, because of commutative property, you might end up having the same subgraph in 2 different nodes of the branch and price tree. And so since quantum resource might be costly, it is better to optimize the use of them. And so we avoid exploring the same graph twice. And so if we see that we already analyzed that subgraph, then we won't explore that direction anymore. And finally, yeah, this is just a summing up of all the elements. We just lack one, the last one, which is very simple. We need a way to stop. We cannot explore we need to find a way to retrieve our best solution. And there are 2 possibilities. Either we stop by optimality, so we have explored all the branch and price tree, and we have no more solution to explore. or we can go for a heuristic approach and decide to stop when we believe we explored an enough number of the branch and price trees node. In our case, we set up these limits up to 20 nodes, but actually we never met that limit. So with all these elements, we have our hybrid algorithm, and we were able to test it. So we have a few results. This first slide here are results done on emulation. So classical resources emulating the quantum system. You have here the comparison among three methods: the hybrid column generation, that was the work carried on by Pasqal, the BBQMIS, which is instead the branch and bound method that was previous work carried on by LINKS, and instead the quantum classical branch and price, which is the algorithm I just explained you in this last minutes. And the key message in this slide is that the branch and price was better than both algorithms, both in terms of optimality than in terms of resource usage. The tables on the left shows you the percent of success. So you can see that the QCBP algorithm is the one that reaches optimality the most of the time over our data set. Was made of graphs with 10 up to 16 vertices, and for each of these number of vertices we have 20 samples. So it's basically 120 graphs. And also the relative gap is instead the number of, this is the optimal solution computed with a classical solver compared to the best solution found by the quantum methods. Also in this case that we can see that we only have like one or two instances in which the hybrid, the QCBP algorithm couldn't find the optimal solution, but it was just like one color more. So it is a very performing algorithm. The plots on the right instead are in terms of quantum resources needed to solve these problems. The upper, the plot above is for graph samples which are actually unit disk, which means that we were able to represent perfectly in the QPU the connection among the vertices. Those for which unit disk samples label is false, it means that maybe some of the edges were missing, or some of them were more represented by the Rydberg blockade effect. So this is also important because it might not be so trivial to be able to provide a unit disk representation of your graphs. And you can see here the scale on the y-axis is logarithmic. And you can see here that the range and bound algorithm was the one requiring the most number of shots. So it was the one requiring the most usage of the quantum resources. Hybrid column generation was instead very well performing in terms of QPU usage, but it was a bit less performing on the optimality. And QCBP instead, it is like it has the best performance in terms of optimality, but also it is very conservative in the usage of the QPU. So it is a very good compromise. And then we can close with results on the quantum machine. We started with a small sample, so you can see here on the bottom left of the slide the arrow graphs, which has 10 vertices, and above you can see the path that was run on the machine, and on the right you can see the histogram. This is an example of the kind of solution you can get from the QPU. So since this is like a system which has some kind of probability distribution, you don't get just one solution. You need to sample more solution from it, and at the end you end up with an histogram where each bar of the histogram is a possible solution in terms described by a bit string. So you have a bit string with 0 and 1s, 1, and that corresponds exactly to the X solution of your partial subproblem. And so you can filter those and see those that are actually independent sets, and use them to feed to your master problems. Also, in this case, here you can see on the green boxes that we found a three colors, which are the ones reported here. And so this is, yeah, my final slide here, just a recap. You have here a scheme of the branch and price algorithm. It is a hybrid quantum classical approach with a good balance between what is quantum and what is classical. We were able to exploit the structure of the problem in such a way to find a proper role to quantum computing. And it is also a kind of approach that can be extended to other problems. You just have to figure out where it is better, where it is a better fit for the quantum part. And so with that, I think I can close. I hope to be to have been enough clear. In any case, I will be able, like I'm here available for possible questions. Thank you.
Thanks to you, Chiara. It was really a nice presentation. Thanks a lot for these insights. I see a lot of very positive reactions, so happy to see that. And now it's time for your questions. So if you haven't done it yet, you can share your questions in the questions feature of the platform. And Chiara and Yassine are here to answer all your questions. So I will start with a questions. I see that I think we can check. Yes, we can start from this one. So Chiara or Yassine, you decide who will take that. If someone wanted to explore potential use cases inside their own company, where would you suggest to start?
I don't know, I can start answering, then if Yassine wants to add something more, you can just please feel free to jump in. I would say like start to look where like classical solutions start having troubles. We all know that finding quantum advantage is very hard and can be very dependent on the kind of instances you're trying to solve. So maybe try to find a problem which is generally hard. And I know that sometimes it might seem easy, but it is not, because maybe you can still improve your classical part. So it's very difficult to find a proper problem. But yeah, I'll still stick with try to see where the classical computation starts having a lot of troubles to seek for real advantage.
Thank you, Chiara. Yassine, if you want to add something, just stop me, or I go to the next question. All right. So maybe you can answer this one, Yassine. Where do you see this kind of hybrid approach heading in the next few years?
For sure, this question will be very dependent on the evolution of the technology. Okay, so for example, if we talk about Pascal's technology, for now we have global addressability on X and Z gates, so omega and delta, if we speak about the parameters of the laser. And I invite people here to join our open webinar in June 17 about the public roadmap of our technology. So we will speak about this kind of information and how the technology will evolve in the next years. And for sure, if we can evolve the number of qubits, and if it will be possible to have local addressability, then it will be much more easier to represent and encode several types of optimization problems at scale. Then, of course, we can expect a given advantage.
All right. Thank you so much. I see other questions very similar to actually what Chiara and Yassine already answered. So there is a lot of interest in terms of use cases. So you guys already answered. Then I see another questions from Giovanni Paleari. So for graphs which are not natively unit disk, how many qubits do you need to embed an n-variable problem? Do you need to embed an n-variable problem? Sorry.
Oh, okay, I can again start answering, and if Yassine wants to add, please just jump in. Actually, in all these samples we tried, we used the same number of qubits as the number of vertices. So independently of the possibility to have an extra representation, we just decided to be conservative on the number of qubits used, and try to use like the less number as possible, so which is the number of vertices in a graph. I'm aware of a few work about say using more qubits to generalize the kind of graph that you can natively represent on the QPU. But still, like up to my knowledge, this kind of other embedding procedure can scale up with like n squared if n is the number of vertices. So they can be, you can reach very easily like the maximum number of qubits that you can have in your QPU. So again, I think it's also like you have to compromise between what is the possibilities of the QPUs and what is the result you can get. Also, in our case, it was not so necessary to have an exact representation of the graphs, because we could see from the results that the classical part of our hybrid approach was strong enough to complement quantum whenever it was not so strong on its own. So also this is, I think, a key message, like try to maybe not go totally quantum. Of course, quantum has to jump in some point, but you have to find the best role for it. So yeah, thank you for the question anyway.
Thanks to you for the answer. So just watching the time, I will move to the next part of the talk, just a wrap up, and of course the last but not the least poll we have in front of us. So in which state are you leaving the webinar? So we will speak quantum till the end, as you can see. So are you fully entangled or collapse into uncertainty? Let's see. You can submit your vote. I see answers coming in. We have a lot of stable states, met expectations, and solid content and insights. So you guys did very well. Happy to see that. And of course, for those of you who still have doubts and still have questions, you can always reach out to us and to the speakers. And I will show you in one slide how you can reach us. So as I mentioned before, we just launched the Quantum Pathways Global Webinar Series, and the next one up, as actually Yassine mentioned, is the Pasqal Quantum Roadmap 2025. So the registration is already open, and a link. If I manage to share it with you, 1 second, it's going to pop up on your screen. 1 second, yes. You can check out the upcoming events within our website, and you can register now on this link. So the Pasqal Quantum Roadmap webinar is going to show you what we have ahead of us in our path towards quantum advantage. The next coming up are going to be in July about fault-tolerant quantum computing strategies and our Pasqal cloud services. That is also available through the cloud marketplace recently. So you can stay up to date for all the events and for all the activity that we are going to organize, also through our community. As I mentioned to you, I am the community builder, so I'm really excited about this project. We are building a space where people engaged with quantum and enthusiasts about quantum can really have a direct impact on its future, specifically its future with neutral atoms. So whether you are a student that wants to learn about quantum computers, or whether you are a researcher already using quantum computers and want to explore new platforms like neutral atoms, or you are working in industry and you want to explore quantum solutions for your specific industry-specific problems, this is a place where you can learn, connect, and collaborate. And I would like to share with you the link to join the community, because I would really love to have you there. And of course, to help you connect with other quantum fellows, we also have a Slack community that you can join through this invitation link. So that was it for us. Thank you so much for being with us today. I really want to thank again our speakers of today. Yassine and Chiara, you did an amazing job. Thank you so much. And thanks to all the attendees for being with us. We recorded the event, so if you want to take a look again, you can do that. And of course, since every feedback, if every feedback counts, we would like to invite you to take a 2-minute satisfaction survey to help us also shape the next events coming up. So thanks again, and we see each other in the next one. Have a nice day, everyone. Thank you.
Thank you.
Thank you.
Bye-bye.
Bye.